Hi, I'm David Wilkins. I'm a senior computer scientist at SRI International's Artificial Intelligence Center. SRI is a not-for-profit contract research institute in Silicon Valley. I got my PhD at Stanford in 1979. My advisor was John McCarthy, who taught my first Lisp class. And immediately after graduating, I moved across to El Camino to SRI's AI Center, primarily because Nils Nilsson was here and I wanted to work with him. My first boss at SRI was Earl Sacerdoti, the author of NOAA. Before NOAA, AI planning was generally search in a state space, and NOAA introduced search in a plan space to AI planning. Inspired by Earl and NOAA, I became interested in solving real-world planning problems and found that this required the use of more domain knowledge and more expressive representations. I divide past research in AI planning into two camps. The first are systems that take a minimalist approach to domain knowledge. They use strip-style descriptions of primitive actions. I call them primitive action planners. The second are systems that focus on leveraging as much domain knowledge as possible. I use this approach in developing the SIPE planning system. On the first slide, we'll see an example of one of the domains that SIPE encoded for planning. It's the response to oil spills. And in this picture, we see several boats deploying boom around an island to protect it from an oil spill. The key point here is that there are multiple boats executing this plan and that it's important to have a sufficient amount of boom to go around the island. On the next slide, we'll see a number of techniques that SIPE developed to address real-world problems. This list was driven by client needs to solve their problems, not by any research agenda. Some of these techniques are now called hierarchical task network planning, and SIPE is known as an HTN planner. The first technique is multiple abstraction levels. Many real problems have distinct natural abstraction levels, making them natural fits for HTN planning. These levels are a powerful way to control the search, and they're a great way to interact with humans because a primitive action strip-style plan at the lowest level of detail can be very difficult to understand. The next item is parallel actions. Realistic domains generally have parallel agents executing activities at the same time, and these agents must coordinate their activities. Parallelism can cause computational problems in AI planners, and some AI planning systems produce only sequential plans. Next is context-dependent effects, which are ubiquitous in real-world problems. For example, if you move an object to a new location, all the objects attached to it or on top of it will move with it. SIPE would deduce these context-dependent effects, whereas in a strip-style planner, you would generally need a different operator for every possible combination of things that might be attached to or on the block. The next two items, constraints and resources, come from the fact that reasoning about numbers are essential to almost every realistic domain. Time is certainly a key element in most plans. Resources also have a specific capacity or must be accumulated in certain quantities. An example of a goal of accumulation is obtaining the boom in the previous example. The planner had to plan to attain enough boom to surround the island, and it had to reason about numbers to do that. SIPE developed heuristics and representations to efficiently reason about actions, which we needn't go into detail here. In the real-world problems, plans never executed as expected, so you wanted to replan during execution to fix the plan. Many AI planners never addressed that problem. And finally, we found a need to have an interactive graphical user interface. SIPE had perhaps the most advanced GUI in AI planning in the 80s and 90s. Interacting with people is a critical aspect of real-world planning. Realistic problems are embedded in the world and aren't precisely defined. They have fuzzy edges. The person almost always knows information the planner doesn't and can use that to help make good choices. Another important reason to have the GUI is that it helps the user understand the plan. A large plan full of primitive actions can be very difficult to understand, and the ability to use the abstraction levels in the GUI and drill down and see network displays is very crucial. So in the next slide, we actually see a screenshot capturing part of an oil spill response plan from the SIPE GUI. We'll look at the top three nodes of this plan. In the top right, you see a blue oval. Blue ovals represent primitive actions that are already in the plan. In this case, the action is to deploy 3,000 feet of boom to the Berkeley eelgrass at time 3. This spill was in the San Francisco Bay. Right before that is a aqua hexagon. They represent goals that need to be expanded at the next level of detail. This particular goal is to get this 3,000 feet of boom located at Berkeley. So looking at the goal immediately below this, it turns out that the higher level goal was to get 9,000 feet of boom to Berkeley. SIPE knew of 3,000 feet of boom in some location, so it split the goal into two. The first one was to get the 3,000 feet there. In parallel, it posted another goal to get the additional 6,000 feet of boom to Berkeley. The entire plan for this oil spill response had a few hundred nodes when it was complete. On the next slide, I'll show you a brief overview of how SIPE produces plans. It has a representation of the state of the world, which you see on the left side of the slide. And that's, for example, where it represents the fact that it knows there's 3,000 feet of boom in some warehouse somewhere. It then has operators that represent actions. These are at multiple levels of abstraction. They represent things about how to transport boom and how to deploy it. Then you have goals and objectives that you're trying to achieve. The plan generator then combines these, and on the right side you see a depiction of how it applies these operators level after level to expand down to the most primitive plan. And when it finally gets a plan composed of primitive actions, then it's ready for execution. And the plan executor will then take over, and if replanning is needed, it will cycle back and give some new goals and give the new beliefs and constraints that represent the world. This concludes my description of the motivations behind SIPE. For more information, on the last slide, there is a URL to the SIPE homepage and to my publications homepage. Thanks very much for your attention.